Welcome back to an introduction to real analysis. We continue going section by section. We're now in chapter 2, section 5, series. So a fundamental object in mathematics, series. So we're finally getting around to it. In fact, when the foundations of analysis were first being developed, one of the primary motivations was to understand series. Why are series so important in understanding analysis? So an example is solutions to differential equations. Solutions to differential equations are often given as series, and in many examples it is the easiest way to find solutions to differential equations. And differential equations really form a basis for most, if not almost all, of modern science. So let's get to the definition. Given a sequence xn, let k be a natural number, we denote the kth partial sum, s sub k, as the sum as n goes from 1 to k of x sub n. So you simply add up the first k terms of the sequence. That is a partial sum. If the limit of the partial sums exist, we say that the series converges to S, and we denote it as a sum going from index 1 to infinity. In other words, adding up, in air quotes, all the terms of the series. Observe, we're not really adding up all the terms of the series. We are adding up finitely many and then taking a limit of those partial sums. So this is the definition of a series. If the sequence of partial sums doesn't converge, we simply say the series diverges. Okay, so our definition is that this series is the limit of the partial sums. Now we only can write this equality if the limit on the right actually exists. If a series doesn't converge, the right-hand side doesn't even make sense because there is no limit. So be careful when you write this series notation. It can mean a notation for the series itself, asking does the following converge or not, or you could be specifically denoting the limit of the partial sums. So it's both at the same time a formal object which may or may not be a real number, or it can be a specific real number, the limit of the partial sums. This is a fairly minor distinction in practice, but you should be careful of the distinction between the two ideas. A formal object, a limit which may or may not exist, versus the actual real number that is the limit. So it's sometimes convenient to start series at a different index. So if we wrote the sum as n goes from 0 to infinity, or the sum as n goes from 3 to infinity, these can simply be re-indexed. Here, if I wanted to start at index 0, you could imagine it starting at index 1 and subtracting 1 from the index. And if you wanted to start at index 3, you could start at index 1 and add 2. So we can maintain the original definition, always starting at index 1, and just re-index series. But generally in practice, everyone understands that if you write a series starting at whatever arbitrary index you want, you mean the sums starting at that index, partial sums must then end at some later index, and you still take a limit. So convergence of the series is still by definition convergence of the partial sums, where you can simply adjust the starting index if desired. Be careful, however. So it's common to write the series, the sum as n goes from 1 to infinity, as x1 plus x2 plus x3, and then ellipsis. So the ellipsis indicates a series that keeps going, not a simple sum. Do not use this notation too often. So we will avoid using ellipses whenever it's at all convenient to not write them, because the ellipsis, this sort of and so forth, is a common way to sort of trap yourself into some false thinking. It's a very informal way of writing things down and often leads to mistakes. So generally, almost without fail, an ellipsis is shorthand for a limit taking place. And hopefully, as the last two chapters have pointed out, limits can be kind of tricky. And we're just getting used to working with them to begin with now in a formal context. So when we can at all avoid doing so with our notation, we're not going to use this ellipsis as a way to paper over when a limit is happening. So let's get to an example. Take a look at the series. The sum as n goes from 1 to infinity, 1 over 2 to the n. This series doesn't just converge, it specifically converges to 1. So let's recall the actual definition of series convergence that will presumably be important. First, we're going to prove by induction that for every k, the kth partial sum is 1 minus 1 over 2 to the k. Now for k equals 1, we have a pretty straightforward partial sum. There's a single term. It just consists of 1 over 2 to the n when n equals 1. That's a half, which is in fact 1 minus 1 over 2 to the first. So our claim that s sub k is 1 minus 1 over 2 to the k does in fact hold when k is equal to 1. Now let's assume that we have proved this claim for some k and look at the next partial sum. So the k plus 1 partial sum goes from index 1 to k plus 1. As is typical in these inductive proofs involving sums, we take the previous partial sum and manually add on the next term. We've inductively assumed that this partial sum is 1 minus 1 over 2 to the k. And now you simply leave the 1 alone and note that minus 1 over 2 to the k plus 1 half that quantity, this 1 over 2 to the k plus 1 is 1 half times 1 over 2 to the k, is indeed minus 1 over 2 to the k plus 1, establishing inductively that our claim holds for all k. So we've proven a nice formula for our partial sums. Well, according to definition 2.5.1, all we have to do now is take a limit. A pretty easy way to do this is to note that by subtracting the 1 over to the other side, we simply have the 1 over 2 to the k. If we're taking an absolute value, we can ignore the minus, and 1 over 2 to the k does go to 0. Therefore, since the absolute value of sk minus 1 is converging to 0, sk must be converging to 1. So according to definition 2.5.1, we finished the proof of example 2.5.4. The same technique, incidentally, with some pretty minor modifications, can be used to prove the following proposition, the full proof of which is left as an exercise. So proposition 2.5.5 has to do with what are called geometric series. For any r in between, but not including plus or minus 1, the sum as n goes from 0 to infinity of r to the n is 1 over 1 minus r. Again, the proof of this is left as an exercise. Let's talk about tails of series. So the terms of a series after a specific index are called the tails, much like the tails of a sequence. So specifically, for the sum as n goes from 1 to infinity of xn, the n tail is given by the sum as n goes from capital N to infinity. Less frequently, the partial sums may be called the heads of the series. Note that the partial sum is the sum up to a certain point. The tail is the sum after a certain point. So tails versus heads. That notation is a lot less common than partial sum. So let's get to a proposition about these tails. Take a series and let capital M be a natural number. Then the original series converges if and only if the tail beginning at index m converges. And this must hold for every natural number m. Okay, so let's prove it. Suppose you have picked an m. Now for any k bigger than or equal to m, we can write the following. The kth partial sum, instead of going from index 1 to k, go from index 1 to m minus 1 and then from index m to k. Observe that this term here is just the m minus 1 partial sum. Now if we subtract that over to the other side, we can state that the sum going from capital M to k is one partial sum minus another. Now observe that s sub m minus 1 is a constant. We began this by picking m to be a natural number. So if we take a limit as k goes to infinity, since this is a constant, this limit exists if and only if this limit exists. So one side converges as k goes to infinity if and only if the other does. Moving on to the next definition, this one is quite straightforward. You can call a series Cauchy or call it a Cauchy series if the sequence of partial sums is a Cauchy sequence. So proposition 2.5.8, the series is Cauchy if and only if, for every epsilon, there is a capital M, so that for every index past that point and k past that one, the partial sum going from index n plus 1 to k is less than epsilon in absolute value. Let's take a look at the proof. So the sequence of partial sums is Cauchy if and only if they converge. Recall that a sequence converges if and only if it is Cauchy. So the series converges if and only if it is Cauchy. Recall that the definition of series convergence is if the partial sums converge as a sequence, and a series is called Cauchy when its partial sums form a Cauchy sequence. So this is immediate just as a term of definition. So by definition, the series is Cauchy if and only if, for any two indices past capital M, the kth partial sum minus the nth partial sum in absolute value is less than epsilon. This is merely stating that the sequence of partial sums is a Cauchy sequence. Now, if I further assume that k is larger than n, what we have here is the sum going from 1 to k, take away the sum from 1 to n. What's left behind are exactly the terms from index n plus 1 to k. So this is not much of a proof. It's essentially by definition. We have called a series Cauchy when its partial sums are a Cauchy sequence, and a Cauchy sequence is exactly a convergent sequence. This more or less falls out. Moving right along to Prop 2.5.9. If a series converges, then the underlying sequence must converge to 0. Observe a nice distinction here between the hypothesis and conclusion. The hypothesis is that the series converges to anything. The conclusion is that the sequence underlying that series must very specifically converge to 0. So if the series converges, then the sequence must converge to 0. Let's get to proving. Let epsilon be arbitrary. Because we are trying to prove a sequence converges to 0, we start by declaring let epsilon be positive. But the series converges is our hypothesis. Because it is a convergent series, it must be a Cauchy series, meaning past a certain index m, the distance between any partial sums past that index must be less than epsilon. So we very specifically are going to take two consecutive partial sums. Now, the n plus 1 partial sum would be go from index 1 to n plus 1, in other words, go from index 1 to n, and then add on the next term manually. But this is exactly the nth partial sum. Subtracting the nth partial sum to this side gives exactly that the distance between two consecutive partial sums is the absolute value of a single term of the underlying sequence. However, because the distance between these partial sums must be less than epsilon, the underlying terms of the sequence in absolute value must also be less than epsilon. Because epsilon was arbitrary and positive, it is now proved that the sequence converges to 0. Let's look at example 2.5.10. For any r bigger than or equal to 1 or less than or equal to minus 1, the geometric series r to the n diverges. An earlier exercise was to show that for r between plus or minus 1, the geometric series converges specifically to 1 over 1 minus r. We're now going to show that for r's outside that interval, the series diverges. Well, if the absolute value of r is bigger than or equal to 1, then if I begin raising that to the nth power, the absolute value of r to the n is still bigger than or equal to 1, meaning it is not converging to 0. So, by the proposition we just established, in the contrapositive, if the limit of the underlying sequence isn't 0, either it has a different limit or this limit doesn't exist at all, then this series must not converge. Next example, take a look at the series of 1 over n. This series diverges. This is known as the harmonic series. This is a very important example of a divergent series. So let's prove it. The proof is by what is known as the Cauchy condensation test. A full proof of this convergence test is an exercise, so we're going to work through a proof of this specific example without citing that test by name, but it's more or less what we're doing. A series converges if the sequence of partial sums converges, in which case any subsequence of the partial sums must also converge to the same thing. So we're going to construct one specific subsequence of partial sums and show that it doesn't converge. And if one subsequence of partial sums doesn't converge, then the sequence of partial sums overall can't converge, therefore the series diverges. Specifically, which partial sums are we going to look at? We're going to look at partial sums indexed by powers of 2. So add up the first 2 to the k terms of this series. Now for k equals 0, we simply have the first partial sum, but for k at least as large as 1, you can state that the 2 to the kth partial sum is the previous partial sum plus a whole bunch more terms going from index 2 to the k minus 1 plus 1 all the way out to 2 to the k. So this is just saying that to get the next partial sum in our subsequence, take the previous one and add in all the terms that you would have been missing. Now the terms 1 over n are decreasing. So let's look at this so-called partial tail. It has 1 over n going from this index to that one. Because they're decreasing, every single one of these is at least as large as the last one, 1 over 2 to the k. So looking at this piece of a tail, every single one of these is bigger than or equal to the last term in that tail, 1 over 2 to the k. So the next term in our subsequence is at least as large as the previous term in our subsequence plus this new term. But now in that sum, at the very end, the index n doesn't appear. In other words, we are summing up a constant, so you can factor it out. So the next sum in our subsequence is the previous sum in our subsequence plus this constant times this sum of 1. But when you sum up a bunch of ones, you're really just counting how many terms are in there. So if you count from a previous power of 2 plus 1 to the next power of 2, the next power of 2 minus the previous power of 2 plus 1 plus 1. This extra plus 1 comes from a so-called fence post counting issue. If you want to count, for example, from 7 to 9, you count 7, 8, 9. That was 3 numbers. So 9 minus 7 is 2 plus 1. So to count how many numbers there are from this one to that one inclusive, you take the difference, but then you have to add in 1. Just working all of this out, you get exactly 2 to the k minus 1. So summing this up, we'll be counting ones over and over, and you will have exactly this many of them. So the next partial sum in our subsequence is at least as big as the previous partial sum plus this sum of constants, which we've just determined is 1 over 2 to the k times 2 to the k minus 1. But hey, 2 to the k minus 1 over 2 to the k is just 1/2. So in our subsequence, when you go from one partial sum to the next, you increase by at least 1/2. So since S1 was equal to 1, there's just a single term in that partial sum, now we can quickly inductively show that the 2 to the kth partial sum is at least as big as 1 plus k times 1/2. Every time you go to the next partial sum in our subsequence, you increase by at least 1/2. Probably more, in fact, definitely more, but at least 1/2. So along our subsequence, you are at least as big as 1 plus k times 1/2. Since our subsequence contains terms at least as big as k plus 2 over 2, if you let k go to infinity, that definitely diverges. It is unbounded above. So there is a subsequence of partial sums which definitely goes to infinity. Therefore, the partial sums are not converging to a real number. So since the sequence of partial sums doesn't converge, by definition, this harmonic series also diverges. So with the harmonic series in mind, observe that we actually have a concrete example where there can be a sequence going to 0, 1 over n does converge to 0, but the associated series does not converge. We have a result that says if a series converges, then the sequence must go to 0. The converse is not true. Just because the terms of a sequence do go to 0 does not imply that the associated series must converge. Let's move on to proposition 2.5.12. Suppose alpha is real, xn and yn both form convergent series, then the sum of alpha times xn is a convergent series and it specifically converges to alpha times x, and the sum of xn plus yn is also a convergent series which specifically converges to x plus y. The proof of this is actually quite straightforward because we have old results that get us there almost immediately regarding sequence convergence. The partial sums of the xn's converge to x. That was one of our hypotheses. So if I multiply those partial sums by the constant alpha, we now know they must converge to alpha times x. The partial sums of yn also converge to y. So we can rearrange the following. The kth partial sum of x plus the kth partial sum of y is just this sum plus this one. We are using an ellipsis here, but this is a finite sum. There isn't a limit going on here. Because we only have finitely many terms, we can use the associative and commutative properties at will, and I move these around. Instead of first adding up the x's and then adding up the y's, I add up the index 1 terms, then the index 2 terms until I get to the index k terms, but that's exactly this. In other words, the kth partial sum of x plus the kth partial sum of y is the kth partial sum of x plus y. So now we can take a limit as k goes to infinity on both sides and get the second result from this proposition. So this proposition, that constants factor in and out of series convergence and convergent series may be added as you would expect, is basically immediate because series convergence is defined in terms of sequence convergence, and we have these results for sequences. So a useful example of scalar multiplication is extending knowledge of geometric series to arbitrary starting values. For example, if you have the geometric series r to the n, where r is less than 1 in absolute value, if you want to multiply that by the scalar a, you can just bring it into the series. Or you can start at a different starting index. If you want to start a geometric series at a different index, if I factor out r to the k, by re-indexing, since n starts at k, but my exponent is n minus k, in effect we are starting at index 0 and then going from there. This series, again, assuming that the absolute value of r was less than 1, converges to 1 over 1 minus r, and we simply have the r to the k factored out as a constant. So geometric series converge whenever that common ratio is less than 1 in absolute value, even if you multiply by a scalar and even if you start at a different index. Now, the product of two convergent series is convergent. So if you have a series converging to x and a series converging to y, then if you multiply the two series together, it will converge to x times y. But the left side is one series times another. It is not the same thing as this series of products. Even for the second partial sum, we will see we get very different things. x1 plus x2 times y1 plus y2 is just not the same thing as x1 y1 plus x2 y2. There are other terms that are generated. So this product definitely converges to xy. This is an entirely different thing, however. Monotone sequences we've seen are a little easier to work with and a little easier to prove results about. So it's often easier to work with series xn where every xn is bigger than or equal to 0. In this case, the partial sums, by adding up xn's, can only get bigger. The partial sums are monotone increasing. Therefore, the question of convergence of partial sums, because the partial sums are now monotone, boils down to, are the partial sums bounded? And specifically, when xn is non-negative and the partial sums are increasing, we only need to know that they are bounded above. So let's formalize this statement in a proposition. 2.5.13. If xn is a sequence of non-negative numbers, then the associated series converges if and only if the sequence of partial sums is bounded above. There's not much to prove here. The partial sums always satisfy one partial sum is the previous one plus a term. Since xn plus 1 is bigger than or equal to, the partial sums are now monotone increasing, and as we've already discussed, therefore they converge if and only if they are bounded above. Okay, because the limit of a monotone increasing bounded sequence is indeed its supremum, where xn was non-negative, we therefore have the inequality that any particular partial sum is less than or equal to the eventual limit, or the supremum. If we allow infinite limits, this inequality still holds. For example, if I took a limit of partial sums here and got a plus infinity as an extended real number, then any partial sum as a real number is less than or equal to infinity. So what we'll see is that the convergence results for series in this setting are quite helpful in establishing convergence tests for series in general. Next definition. A series is said to converge absolutely if the series of absolute values converges. If a series converges but does not converge absolutely, one says that it converges conditionally. On to proposition 2.5.15. If the series of xn converges absolutely, then it converges. Furthermore, we have this inequality. Now recall that by definition, converges absolutely means this series converges to something. So there's a real number on this side of the inequality. Assuming that, then this series converges and its absolute value is less than or equal to whatever that value on the right is. So how would we prove it? Now that inequality is left as an exercise. It's basically an extension of the triangle inequality, but again, the details are going to be left as an exercise. So we're just going to focus on the first half of this proposition. Establish that the series converges assuming that the series of absolute values converges. Okay, so a series converges if and only if the partial sums converge. That's the definition. However, that sequence of partial sums converges if and only if that sequence of partial sums is a Cauchy sequence. So the partial sums of the absolute values are Cauchy, meaning for any positive epsilon, there's a capital M, so that for two indices past capital M, let's let little n be the larger one, we have this partial sum minus this one in absolute value is less than epsilon. However, this partial sum minus this partial sum is simply the sum going from index k plus 1 to n. Since every term here is non-negative, this sum is non-negative, so this exterior absolute value is not necessary. So what do we have? For any two indices n and k, let's assume n is the larger one, past capital M, this in absolute value is less than epsilon. So here's what we have from the previous slide. But we can also have from the triangle inequality that this absolute value, this is, observe, the nth partial sum and the kth partial sum of the original series without the absolute values. But now this absolute value on the exterior is necessary. We don't really know what's going on with these terms. But by the triangle inequality, because we have finitely many terms here, I can say it's less than or equal to this sum here. So the partial sums of the original series are Cauchy, because what do we have here? We have the sum of the absolute values of xi, which is exactly what we've just established is less than epsilon. So the difference between these two partial sums of the original series is also less than epsilon, meaning the partial sums of the original series are Cauchy, and therefore they converge to something. So suppose you have a series that converges absolutely. Generally, we don't expect these two things to be equal to each other. Okay, just because one series converges and a series of absolute values converges, you don't think they're going to converge to the same thing. Computing one of them doesn't even really help very much in computing the other, except in establishing the inequality that was in the previous proposition. Absolutely convergent series, however, do have a lot of nice properties. For example, you can rearrange them arbitrarily or multiply them together quite easily. Conditionally convergent series, in contrast, those series that converge but do not converge absolutely, do not behave as one would expect very often. So let's take a look at the next section. Now we leave as an exercise to show that this series here converges. What is this series? It's basically 1 over n, the harmonic series, but the numerator isn't 1, it is alternating between plus or minus 1. It's called the alternating harmonic series. Now, as an exercise, show the alternating harmonic series converges. If you've done that, we now have an example of a conditionally convergent series. This series converges, but if you replaced its terms with absolute values, the plus or minus 1 would all become 1, 1 over n, harmonic series already established to diverge. Now earlier, we noticed that a series with positive terms converging, it's not enough to show that the individual term goes to 0. The harmonic series has terms that go to 0, but the series does not converge. So the terms don't just have to go to 0. In a sense, they have to go to 0 very fast. Now, if we know a certain series converges, we can use this next upcoming test called the comparison test to see if the terms of a different series go to 0 fast enough. Now, this test for convergence is very quick to prove. It's not going to take very long, but it really is the foundation for a great many more convergence tests, so pay attention. Here is the comparison test. Suppose you have a series and another, but you have the inequality. First of all terms are non-negative, but the xn's are less than or equal to the yn's. then if the series of y's converge, so does that of x, and if the series of x diverge, then so does y. How would we prove this? Now, the second claim is just the contrapositive of the first. If yn converges, then xn converges. Okay, if xn doesn't converge, yn doesn't converge. Okay, so all we have to do is prove the first. The underlying sequences of xn and yn are non-negative, meaning their partial sums are monotone increasing. Because the yns converge, their partial sums are a converging increasing sequence. They have a supremum. Call that supremum y. So each partial sum of x's is no larger than the partial sums of y's because every single x is less than or equal to y. But these partial sums of y are converging to their supremum. So every single one of them is less than or equal to their supremum. So now we have every single partial sum of x is less than or equal to whatever the series y is converging to, meaning the partial sums of x have an upper bound. But the partial sums of x are also monotone increasing. They converge if and only if they are bounded above, and we've just established they're bounded above. Therefore, the sequence of xn also converges. Not a very long proof, as I said. Let's take a look at what is called the p-test. Let p be a real number. The sum of 1 over n to the p converges if and only if p is bigger than 1. I would remark, sometimes you see this written without the reciprocation, just the sum of n to the p, in which case it converges if and only if p is less than minus 1. But we've written it in this reciprocal form here. Okay, let's prove. First, let's suppose p is less than or equal to 1, in which case we are trying to establish that this series will not converge. Well, if p is less than or equal to 1, then n to the p is less than or equal to n. In other words, 1 over n to the p is greater than or equal to 1 over n. The harmonic series of 1 over n diverges. So we have two different non-negative series. This one, when you add it all up as a series, diverges. So by the comparison test, this one is even bigger. It also diverges. So proof half done. Now let's suppose that p is bigger than 1. The terms of the sequence are monotone decreasing. Since p is larger than 1, we are raising numbers to a power larger than 1. Those are just going to get bigger, so their reciprocals are only getting smaller. So the terms of the series are monotone decreasing. So we're going to proceed similarly to the proof that the harmonic series diverges. Again, we're basically going through what is known as the Cauchy condensation test, and the full derivation of that convergence test is left as an exercise, so we're just going to kind of work through it in this special case. So these terms are decreasing. The 1 over n to the p's are getting smaller, meaning, let's just take a look at some of these terms, but because they are all getting smaller, if I add up these terms, that is less than or equal to, over the same range of indices, only adding up the first term over and over again. So instead of adding up 1 over m to the p, where m starts at 2 to the I and goes up, I'm just going to add 1 over 2 to the I to the p the same quantity of times. But this is just a constant as far as this index of summation is concerned. So I can factor it out of the sum. And as we've seen before, if you count how many terms are in this sum, it would be exactly 2 to the I. These 2 to the i's are going to simplify very slightly. So the key observation here is that we can now transform this into what looks like a geometric series. Again, we're just taking some of these terms added together. We established less than or equal to this. So if I divide numerator and denominator by 2 to the I get 1 over 2 to the I to the p minus 1. And here's a classic trick. 2 to the I to the p minus 1 is the same thing as 2 to the p minus 1 to the I. So adding up some terms of this series is less than or equal to a fixed constant raised to the ith power. Remember, p has already been picked. P is constant here. Okay, here's that inequality we just established. Let's take a look at a subsequence of partial sums. Specifically, the index that we're going to stop at is a power of 2 minus 1. We could write that as going to the previous power of 2 minus 1, plus adding all of the terms that aren't accounted for, that next power of 2 up to this new index. But we've just established that this sum right here is no larger than this quantity. So now the first partial sum we can just compute is equal to 1. Inductively, if I keep doing this out to 2 to the k minus 1, we have that first partial sum plus a bunch of terms that look like this. But this is now a constant to a power that is our new index. So we've sort of transformed these sums into a different partial sum. So what have we established? Our partial sums, at least along this subsequence, are less than or equal to 1 plus the partial sums of this series. But this is a geometric series. I have a sum of something to the index of summation. So if p is larger than 1, that exponent p minus 1 is indeed positive. So 1 over 2 to a positive power is less than 1. So as k goes to infinity, we have a converging geometric series on the right, meaning there is a subsequence of the partial sums of our original series that are bounded above. But the partial sums of our original series were non-decreasing. So if a subsequence is bounded above, then it is converging. However, because the original partial sums are non-decreasing, if any subsequence of them is bounded above, they are bounded above overall, therefore converging, therefore our series converges, completing the proof. Let's talk about it. Neither the comparison nor the p-test tell us what a series converges to. They both give us, oh, under such and such conditions, the associated series converges, but it does not tell us what it's converging to. For example, the sum of 1 over n squared, because that power is larger than 1, it does converge by the p-test. But it definitely doesn't tell us that it's converging to pi squared over 6. That's a true result, but we definitely don't know that at this point. Okay, this is known as the Basel problem. Now, treating the value of a p series as a function of p means for any p larger than 1, the associated series converges, but to what? Call it zeta of p. That's the Riemann zeta function, which you may have heard of before, especially once you then extend that to take non-real or complex values. It's an extremely important function in mathematics, specifically in number theory, although you wouldn't understand why just from seeing it in this series context. It's definitely beyond the scope of this course, and it's pretty weird and interesting that it has anything to do with number theory. Let's take a look at another example, 2.5.18. The series 1 over n squared plus 1 converges. So we're just going to combine comparison and p-tests. This is pretty quick. 1 over n squared converges by the p-test because it's 1 over n to the 2. P is 2. That's bigger than 1. Also, because n squared plus 1 is bigger than n, 1 over n squared plus 1 is less than 1 over n squared. So 1 over n squared plus 1 is less than 1 over n squared, which converges. Everything is non-negative, so by the comparison test, our series converges as well. Let's take a look at what's called the ratio test. Now, for a geometric series, the ratio of two consecutive terms is just r. We're going to combine the geometric series test with a comparison test to derive a really flexible convergence test, one that is used, in my experience at least, more than any other. Here it is then, the ratio test. Let the sum of xn be a series, no term of which is ever equal to 0, and assume that the limit of the absolute value of the ratio of two consecutive terms exists and is L. If the limit is less than 1, the series converges absolutely. If the limit is bigger than 1, the series diverges. If the limit is equal to 1, no conclusion can be drawn. Also, if the limit doesn't exist, no conclusion can be drawn. Let's prove it. First, let's suppose that this limit doesn't just exist, it is less than 1. Because it's a limit of absolute values, note L is a limit of a bunch of absolute values, it's definitely bigger than or equal to 0. So pick an R that is bigger than L and therefore also definitely bigger than 0, but less than 1. Since L was less than 1, there is an R that can be found in there somewhere. Which means R minus L is positive, call that epsilon. Since this sequence of ratios is converging to L, here's a positive number. There's a cutoff point past which the distance from this ratio to L is less than epsilon. Now I have this in absolute value. is less than r minus L, it certainly follows that this absolute value is now less than r. Okay, we can now inductively establish that at least past this cutoff index m, we can do the following. Looking at this inequality that I'm highlighting now, the next term is less than r times the previous term, in absolute value at least. So past that index capital M, simply pull that factor of r out repeatedly. From xm, to get to xn, I can multiply by this nasty looking product. But what's really going on here? When I is 0, you get xm plus 1 over xm. That would cancel the xm and leave xm plus 1. When I is 1, you get xm plus 2 over xm plus 1. That will cancel the m plus 1s and leave an xm plus 2, etc., etc., etc. By the time you list out all of these products as I goes from 0 to n minus m minus 1, if you cancel everything out, you'll be left with just an xn. However, what do I know about all of these ratios? They're all less than r. How many are there? N minus m of them, because it goes from 0 to n minus m minus 1. Because we're including 0, we have n minus m ratios in total. So the absolute value of xn, at least when n is past this cutoff m, is whatever the absolute value of xm is, which is functionally a constant because m is fixed, times this r to a growing power. M is fixed, but n can now be arbitrary, larger than m. So here's what we had from the previous slide. For n larger than m, the partial sums of the series of absolute values can now be estimated in the following way. Take the sum going from 1 to n of absolute values. Peel off the first capital M terms because I really don't know what's going on there. But past that index, I know that these terms are less than this thing right here. So if we just set this first finite sum of finite numbers to be a constant, this is just a constant. Now this sum here, I'm going to re-index to start at index 1 by subtracting capital M from everything. So what do we end up with? The sum from 1 to n of xn is less than this constant plus factor this constant term out, and now you'll end up with just r to the k, as k goes from 1 to a new finishing index of n minus m. We simply subtracted capital M from all of our indices here. Now these sums on the right here are partial sums of a converging geometric series. Remember that the r we picked was between 0 and 1. So these are converging. Therefore, these are converging as well, thanks to the comparison test. So since the sum of the absolute values is converging, the original series converges absolutely, and that's all we needed to claim for the first bullet point. Now let's recall lemma 2.2.12. If L is bigger than 1, then the underlying sequence must be unbounded. However, for a series to converge, the underlying sequence must converge to 0. So if L is bigger than 1, the underlying sequence diverges, therefore the series must diverge as well. What happens when L equals 1? Now, as written in the book, it's not even written. If it's not written there, you wouldn't draw any conclusions. But I'd like to point out that we have established the harmonic series diverges, and we mentioned that the alternating harmonic series converges. However, in both cases, you get that the ratio of absolute values goes to 1. Therefore, one of them has limit 1 and diverges, one of them has limit 1 and converges. So just because the limit of the absolute value of consecutive terms goes to 1, you can definitely get either convergence or divergence. Let's take a look at example 2.5.20. The sum of 2 to the n over n factorial. This converges absolutely. The appearance of factorials in terms of your series is almost always a dead giveaway that the ratio test is going to be useful. So let's apply the ratio test. We don't need to write absolute values because no term of this series is negative. Here's the n plus 1th term. Here's the nth term. This comes up to the numerator. That goes down to the denominator. Now I have 2 to the n plus 1 over 2 to the n factorial over n plus 1 factorial. simplifies to 2 over n plus 1. As n goes to infinity, that's 0. So, did this limit exist? Yes, it was 0. That's definitely less than 1. So the series converges absolutely. So let's review everything from this fairly lengthy section. We defined convergence of series in terms of convergence of a sequence of partial sums. So many students who've studied a little bit of series before have probably seen this definition. But our focus here is on proof rather than mere computation, so clearly stating the definition was definitely an important place to start. We then proved some familiar convergence tests, like the p-test and the ratio test. Note that they relied on the more fundamental comparison test and geometric series test. When you first study convergence of series, you tend to focus on the ratio test as the most useful thing that you use over and over. Here our focus is on proof, so it's worth stating that the comparison test and the geometric series test were really the first building blocks that we established. The p-test and the ratio test came out of those.